This is Chapter 1.1, Patterns and Inductive Reasoning for Geometry. Please be sure, students, that you take notes as if you were in class. Some things you will need to pause and solve some problems on your own. To begin, describing a visual pattern. When you see something, you need to begin to immediately look at the pattern and see what you notice, what's happening, what's going on. For example, in the first diagram, we see one box or one square. In the second pattern, we see the three boxes. And the question becomes, once we look at patterns 3 and 4, what happens in the fifth pattern? Well, if you want to make a guess, you can hit pause and do so. But I'm going to continue on. So pattern 5 looks like this here. In this particular pattern, we see that there are 5 squares in the bottom row. Now you can try it on your own in this next set. Sketch the next figure that you would see after looking at the first, second, and third pattern. You can hit pause and try that for yourself. Now, after you've done that, you can clearly see what the fourth pattern should or would look like. The red on the right. Every last one of the pictures have been turned, moving counterclockwise, going from 1, we turn it counterclockwise to get 2, and then counterclockwise to get 3, and then finally one more time for another counterclockwise turn to get the 4th. Alright, describing a pattern is simply the sequence of numbers. You can predict the next numbers that you're going to see. Look at the first pattern here. In this particular pattern, you're going to see 1, 4, 16, then 64. The question is, what should the next number be? And if you've guessed 256, that is correct because each number is 4 times the previous number. Okay? So 1 times 4 is the 4, then the 4 times 4 is 16, and 16 times 64 is, and then the 64 times 4 is the 256. Let's look at the next one, B. -5, then -2, 4, then 13. Let's describe this number pattern. How do we go from -5 to 2? Are we multiplying? Are we adding something? Okay? And if we're adding, what are we adding? You may be saying +3 here. How do we go from -2 to +4? Looks like a +6. Okay? And then from 4 to 13, what are we doing? You've got to look at the different ways that you go from one set of numbers to the next. So what would the next number be? It's actually going to be 25 because you add 3 to get the next number. So exactly as we stated, to go from the -5 to the -2, excuse me, we add 3. To go from -2 to +4, we add 6. To go from 4 to 13, we added 9, and it looks like we're adding 3 more onto the previous pattern. So the last one was +9, that means the final one will be +12. And 13 plus 12 will give us 25. Again, you're looking for a way to describe the number pattern. Okay, so if you added 3 to the second number, as we did in the -2, okay, then you add 6 to get to the third number. Then add 9 to get to the fourth number, and so on and so forth. You will begin to see your number pattern and be able to describe it. Now you can try it by predicting the next pattern here. You can hit pause and then try it for yourself. 17, 15, 12, 8. What will be next? Pause. If you guessed that the next number should be 3, you were correct. Okay, the pattern suggests that you subtract 3 from the first term to get to the second term. So 17 minus 2 will give you 15, then 15 minus 3 to get the 12, and then the 12 minus 4 to get the 8, and then so on and so forth. You would subtract 5 from the last to get the fifth term, which is the 3. All right. This chapter looks at inductive reasoning. In inductive reasoning, you have to do a couple of things. First of all, to begin, we're going to jump down just a little bit further and look at conjectures. What conjectures are, is kind of like in science. Conjectures are unproven statements based on your observation of what you've seen. So it's kind of like a hypothesis, okay? Something you've looked at in the past. So a conjecture is when you look at a number pattern or you look at a pattern of designs and you try to figure out what the next step should be, you make a conjecture, or a hypothesis is what it would be called in science. After you make a conjecture or a hypothesis, you begin to look for patterns, things that you notice. You've got to look for patterns. What do you see happening? When you begin to look for patterns, that's called inductive reasoning. You're looking for the pattern in the conjecture. The conjecture is the hypothesis type thing that you would do in science. And then you would use inductive reasoning. You will look for the pattern after you made a conjecture to figure out what comes next, what should be done afterward. Okay? 3 steps in using inductive reasoning. The first step, look for a pattern. What do you see happening? Always look for a pattern, like we did back here. We looked at step 1. What pattern did we see? We made a conjecture, okay? Look at second pattern. We looked at the third pattern. We looked at the fourth pattern, and then we used some inductive reasoning to determine what should come next in the 5th pattern. Okay? So here we are. Step 1. Look for a pattern. What's going on? Step 2. Make a conjecture, okay, based on what's not proven. Remember, conjectures are not proven, just like a hypothesis is not proven, okay, based on your observations. So after you look for the pattern, make a conjecture, hypothesis. Number 3, we use logic from math to verify. So use some logic to verify what you've been given. All right. Making a conjecture to solve a problem. The conjecture or the hypothesis for this particular one is the sum of the first n odd positive integer is what? The sum of the first n positive integers is what? Okay? So here we have a solution. In our solution, we begin to look at, and if you haven't done so already, you want to open your book. I'm looking at example 3. Some examples of the first odd positive would be, here's our first odd positive. We have 1 equals 1 squared. Okay? The second one, we look at the sum of the first 2 odd positive integers. So 1 plus 3. The first odd number is 1. The second odd number, remember odd, not even, is the 3. The sum of the 2, because we're adding, sum is equal to 4. And how do we get this 4? 2 squared. So what would the third pattern look like in this conjecture and our hypothesis? Well, if we're given this information, the sum of the first 3, remember odd positive integers, positive, no negative numbers. And when we look at that, we have here 1 plus 3 plus 5, which does equal 9. So we're looking at our conjecture and we're thinking 3 squared here. And the next one, How do we do this? The sum of the first four odd positive integers is equal to 1 plus 3 plus 5 plus 7, which is a total of 16. And we get that by taking 4 squared. Now, based on our conjecture or hypothesis, we write what we believe the theory is. In this particular case, we believe that our theory says the sum of the first n odd positive integers is n squared. So it looks like over and over and over and over again, we always take some number squared, regardless if the number is odd or even. Okay? So the n here, this time n was equal to 1. N was equal to 2. This third one, we had n is equal to 3. And then finally in this fourth one, n, the number was equal to 4. And we squared all of them together. Conjectures are always true if they work in all cases. Conjectures are true if they work every single time in all cases. Whenever a conjecture is not true, you have to prove it as false with a counterexample. A counterexample makes your conjecture false. Let's say somebody comes up with a hypothesis or conjecture stating this here. The product of two numbers is positive. Then the two numbers must both be positive. Well, that's false because two negative numbers can give a positive answer. Okay, and if you got stuck, just hit pause again. Look at the first top portion. The product of two numbers is positive. Then the two numbers must both be positive. Why is that false? Well, first of all, we think 2 plus 3 is equal to 5. I got a positive answer of 5. If I did 3 plus 7, that's 10. Those are two positive numbers, 3 and 7. Or 5 plus 11 is 16. Okay? I added both of those numbers and still ended with the positive 16. But this conjecture is false because of this statement here. I can do a negative 3 plus a negative 2, which gives me a negative 5. Therefore, making this statement false. Once I make my conjecture or hypothesis false, I've used a counterexample. A counterexample. And this concludes 1-1.